In this video, I'm going to review two current sensor block detector boards I recently purchased from MGP in Sweden. They are significantly cheaper than most other products, so let's find out how good they are. Welcome to the IoTT channel. I am Hans Tanner. In video number 38, I gave an overview on model railroad control devices and did a classification of typical sensors. As we have seen, we can distinguish between at-point and in-area sensors. At-point sensors trigger when a train or a part of a train, typically a single car or a single axle, passes a specific point. In order to do block occupancy detection, we can count the trigger pulses in both directions at each end of a block, subtract them from each other, and finally conclude whether the block between two sensors is occupied or free. In-area detectors, on the other hand, provide a way to measure the presence of a train anywhere in the monitored block, but typically without information about the exact location within the block or information about the number of cars or axles. Both categories, as we have seen, have their advantages and disadvantages depending on the application. The standard way for in-area detection is using a current sensor, and most system manufacturers provide their own line of products in that area. However, there are also independent manufacturers who offer block detecting current sensors, quite often with some cost benefits compared to the solutions of the system manufacturers. But then, how good are these sensors and how easy is it to integrate them into our model railroad control system? One such manufacturer I recently came across is MGP in Sweden. MGP stands for Moellehem Gardsproduktion. You find the link to their webpage in the description below. Moellehem, or MGP, offers some N-scale rolling stock, mostly featuring Swedish railway prototypes, some signal masts for modeling Danish and Swedish railroads, and quite a variety of electronic modules like drivers for LEDs, power supply boards, and more. What caught my attention, whoop, you hit me a like, thank you. What caught my attention was their selection of current sensor boards. Their offering makes use of two of the technologies discussed in video number 38, transformer and diode-based current sensing. And what really made me interested was that their diode-based detector board is featuring an optocoupler output to the control system, something I have not seen in other manufacturers' offerings. So I ordered 4 of the occupancy detector 8 diode boards and 1 occupancy detector 2 board. I personally prefer diode technology because of the better sensitivity compared to the transformer boards, but then there are also areas of application, for example reversing loops, where transformer-based detectors are more suitable. As we have seen in video number 38, one size does not fit all. The ordering process using the MGP webpage was simple, and I was able to pay directly from my PayPal account. The Swedish krona to dollar exchange rate is about 12.5 to 1, so the cost of a diode-based 8-channel board is about $10.50, and the transformer-based 2-channel board is around $7.70. And even if you have to add the cost for an interface board providing a connection to the command control system, these prices look promising. I chose standard shipping for my order as there was no urgency and I'm a cheap guy anyway, and I received the products about 3 weeks after placing the order. The first thing I noticed after opening the package was some damage on 3 of the 4 diode-based boards, as one of the capacitors got disintegrated from the board. Luckily, the boards were all in individual plastic bags, so the missing capacitors were just lying in the bag and not lost in space. My first attempt was trying to apply some soldering paste and reheat them with a hot air gun, but to my surprise that would not do the trick. The capacitor was still loose. So I ended up using a good old soldering iron and soldered them on the board. Problem solved. However, it is strange that components come loose on a soldered board. Normally, a mechanical impact big enough for this would cause some damage to the component, and the soldering pads would be damaged as well. Since none of this was the case, I think there was a problem with the original manufacturing process. I notified MGP about the problem and they were already aware of it. Here is the reply from Anders Boström of MGP. To start, I connected the board to a yellowhead according to the documentation on the MGP webpage, which at the time was only a few lines of product description. Talking about documentation, in the process of doing the review, I had several questions and observations I emailed to Anders at MGP. He was always very quick to respond, and as part of the process also improved the documentation for the sensors. Just a few days ago, he has posted a draft of the English manual for both sensor types on the MGP webpage. I leave a link in the description below. As it turns out, this board and the yellowhead are a total fit. It almost seems the board was made for the yellowhead. I used the 12-pole ribbon cable to connect to the yellowhead on one side and connected the other end of the cable to the 8-pole plus ground screw terminal on the sensor board. The optocouplers of the board provide an open collector output, so they can directly be connected to the yellowhead and drive the input lines. I used the opportunity to add a sensor input option to the IoTT software so that the input lines can directly send input report messages. I then set the first 8 input lines of the yellowhead as inputs 101 to 108. Then I configured the first 8 LEDs of the LED chain to display the occupancy status, dark for free and yellow for occupied. With that, I was ready to actually test the inputs. First, I hooked up the DCC signals to the screw terminal on the sensor board. Then I used the 10K resistor between DCC-B and the output lines 1 through 8 to simulate a locomotive on the track. The current sensors worked as expected and the LEDs came on for each channel. I then wanted to know what maximum resistor value could be reliably detected. To test that, I connected a 10K potentiometer in series to the 10K resistor and turned it all up. No LED came on, so 20K is definitely too much. Then I gradually turned the potentiometer down and the LEDs came on at a value of about 15 kiloohms. I verified that for all 8 channels and it seems that 15 kiloohm is the maximum value for a reliable trigger every time the DCC signal is connected to the resistor. So detecting a locomotive never should be a problem and cars can be fitted with a 10K resistor and also be reliably detected. Looking through the draft manual, I noticed that there is now a newer board design than the one that I have received. The new version has some additional solder holes where parallel capacitors to the measuring diodes can be added. The idea is that the user could reduce the sensitivity of the detector if needed. What the parallel capacitor does is reducing the voltage across the diodes for very small currents. Such small currents could be caused by capacitance created by the wiring of the track or the track itself. Basically, if you have 2 wires in parallel, they form a small capacitor. And from an electrical point of view, any piece of track is nothing but just 2 wires in parallel. The resulting capacity can be calculated using this formula. And luckily, there is a web page available that implements it, so we only have to enter the numbers. As it turns out, N-scale track with only 9 mm distance between the wires has a capacitance of about 10 picofarads per meter. I checked my components box and found 3 capacitors I could use for testing, With values of 22 picofarads, so about 2 meters of drag, 480 picofarads, or roughly 50 meters of drag, and 106 nanofarads, which is equivalent to about 10 kilometers of drag. Both lower values caused none of the inputs to trigger, while the large value triggered all of them. So I don't know where the threshold is exactly, but it seems that 50 meters of N-scale drag per block is not a problem. And larger gauges are about the same. Maybe even more critical than the drag is the actual feeder wire. In order to keep the capacitance in limits, you should keep it as short as possible and ideally use two individual wires for two poles, separated by about the same distance or more than the rails on your track. Using a double conductor cable is less ideal with regards to capacitance. So having the possibility to add an extra capacitor to reduce sensitivity of the board is a nice feature, but as Anders wrote in one of his emails, most people don't need extra capacitors. The more interesting characteristic of a diode-based current detector board is the maximum current it can handle. Things to look at are the diode characteristics and the width of the traces on the PC board. The width of the PCB traces in this case is about 2.3 mm, which is sufficient for currents up to about 4.5 amps. The diode type A34 on the board is a 3 amp Schottky rectifier diode with a forward voltage of 0.4 volts, which results in a nominal power dissipation of 50% of 1.2 watts at 3 amps drag current. Looking at that data, I would expect it to get warm to hot at the nominal current of 3 amps, but of course I had to try it for myself using an automotive bulb as high current load. I used a 0.3 ohm series resistor to measure the current through the bulb by monitoring the voltage on each side of the resistor on the oscilloscope. The voltage drop was about 1 volt, which indicates a current of about 3.3 amps, about 10% above the nominal current. After a few minutes I noticed a slight smell, but as it turned out it came from the series resistor, which of course had to dissipate more than 3 watts. I touched the diodes on the sensor board with my finger. They were hot, but not terribly hot, probably somewhere around 60 or 70 degrees. Too hot to keep the finger on permanently, but not hot enough to get burned immediately. So it looks like the sensor board can output 3 amps without problems, which makes it suitable for N and HO scale applications, but probably not so much for my garden railroad. Overall, I was very pleased with the findings and would recommend using this board. The electrical isolation provided by the optocouplers and the seamless integration with the yellow hat to send block detector messages to Loconet or JMRI make it a reliable and cost-effective solution. Next, I tried to hook up the transformer-based 2-input board to the second port of the yellow hat. Connecting it is straightforward, and for this product there was even some sort of a manual available on the MGP webpage. Unfortunately at that time it was only in Swedish, but of course that's no real challenge thanks to Google Translate. The plus and minus wires are connected to the power supply connector of the board, and the input wires go to the output connector. Next, there is a jumper for each output that is used to select the output style. If the jumper is on pins 1 and 2, the board outputs a defined voltage level, 5 volts when a locomotive is detected on the track, and 0 volts if the track is empty. If the jumper is set on pins 2 and 3, the output is switched to open collector. According to the manual, it is pulled to ground if a locomotive is on track, and open if the track is empty. For using it with the yellow hat, I set both jumpers for open collector mode and then connected the board to the yellow hat port connector. Much to my surprise, both indicators on the yellow hat input screen immediately showed track occupied, even as there was no wire run through the transformers yet and the LEDs on the board were dark. Why could that be? I first tried to adjust the sensitivity by changing the potentiometer position, but this had no effect. I then measured the resistance between output and ground of the board, and it was at 0, so the output was obviously active, even though, according to the manual, it should be high impedance if no current is detected. I decided to try to find out and see what happens if I actually run track wires through the transformer. As suggested in the manual, I ran a track feeder wire through the transformer and then adding a second loop. Then I removed the output connectors from the yellow head just to be on the safe side, and with the board powered with 5 volts, I connected a 4.7K resistor to simulate a locomotive on the track. As soon as connected, the occupancy LEDs on the board came on, indicating a current flow on the track. So apparently the board was working, but for some reason the output signal I got for the empty track was wrong. Was it simply reversed? To find out, I hooked up the yellow head again and repeated the load simulation with the resistor, and indeed the output went to high impedance and the yellow head input field on the screen showed free as soon as current was flowing through the coil. So as it seems the output is working, but the logic was just the other way around compared to what was described in the manual. And even more irritating, it is also just the other way around compared to the diode-based detector. Because I wanted to be sure about my findings, I had a closer look at the hardware of the board. As I figured out, the jumper connects the output to one of 2 pins of the NE556 timer chip. In position 1-2, it is connected to the out pin, which is an inverter output and has a defined voltage for both logic states. In position 2-3, the output is connected to the discharge pin of the timer, which according to the schematics is an open collector output. And according to the schematics and the description in the NE556 datasheet, the open collector discharge output is low impedance if the out signal is low and high impedance if the out signal is high. So exactly the opposite of what was stated in the manual, but in line with my findings. Of course, that is not very convenient if you want to use the signals for layout automation. To make it somewhat easier, I went ahead and added an inverse logic checkbox on the setup of the yellow head, so that the problem can be resolved by a simple software configuration option. I also emailed Anders about these findings, and he confirmed that the information in the manual was wrong. As mentioned, he since published an English draft manual, and if you check, the description is now correct. But of course, the transformer sensor still works with a different logic than the diode sensor, which is somewhat odd. I then went on and tested the sensitivity of the transformer output. First, with 2 wraps of wire around the coil. I found that the resistor of about 8 kilo ohms can be reliably detected. For a 10K resistor, I found it is better to use 3 wraps, but then it works as expected as well. So let's summarize the findings of my quick review of those 2 products. The occupancy detector 8 diode I would consider a very good current sensor for N and HO scale, but not necessarily for G scale because of the limited current output of about 3 amps. The sensitivity is good. It can reliably detect the 15 kilo ohm resistor. It is featuring an excellent concept not seen on similar products because of the galvanic separation of DCC and information circuitry. It is very easy to connect to control boards thanks to the open collector outputs of the optocouplers. With 8 channels, it is a perfect fit to be combined with one of 4 input ports of the yellow head. It is reasonably priced and allows for total cost for block detection in the area of about $3 per block. The current batch though might have a problem with soldering a capacitor. However, this is an easy fix if you have a soldering iron. The occupancy detector 2 with transformer is a good sensor for all scales, as the track wire is simply wrapped around the coil and the sensor does not have to handle the track current. It has an acceptable sensitivity, particularly if the wire is wrapped around the coil 2 or 3 times. It will detect the 10K resistor without problems. With 2 channels, it is a good and relatively economic solution for situations where a transformer-based sensor is more suitable. I think the major problem of the board is the open collector output. The output logic was reversed compared to the instructions in the manual, something that now is fixed. And it is also different from all other open collector sensors I am aware of. This may cause problems with the integration in a layout control system unless the software allows for simply changing the input logic somewhere in the process. I really hope that MGP is going to add the extra transistor that is needed to reverse the logic of the output so that it behaves like open collector outputs on other products. Sensor active, output low. I also would like to point out that MGP is very easy to work with and answers questions about their products within a short amount of time. And that's it for this video. I hope this information was useful or at least interesting for you, and you now have a better understanding how these 2 sensors could help to implement block detection on your layout. In the next video, I will show you how to use these detectors along with the yellow hat and some LEDs to create an automated block signaling system. Make sure you subscribe to the channel and click the bell icon so you will be notified when it comes out. Thanks for watching and see you next time.